Hello, everyone. My name is Aviral Kumar, and I'm a new assistant professor in the ML department and the CS department. My research broadly focuses on the topic of building machines that can make intelligent decisions. And to be able to do this, I focus on the kind of techniques of reinforcement learning, uh, studying their interplay with foundation models, applications in robotics, and many other domains out there. So, broadly speaking, I am interested in the question of sequential decision making. And to me, this concretely boils down to building machines that can make good decisions, decisions that are potentially better than the data that was used to train these machines, as well as the behavior from these machine learning models should be such that these machines can plan their behavior on the fly, interact with the world, and use the interaction to reduce their uncertainty and improve their behavior on the fly. Now, this sort of desiderata and are very much needed in many problem domains, such as in robotics, in just LLMs or foundation models interacting with humans or tools or the open web out there, as well as in sort of safety critical problems such as healthcare and many other scenarios, such as education as well. In all these cases, we need models and machine learning models that satisfy these desiderata. So to be able to answer this question, my research sort of focuses on the starting point of classical reinforcement learning. So reinforcement learning is this paradigm of learning where you typically consider a learner interacting with an environment by making decisions or taking actions. And as a result of taking these actions, it observes consequences which it uses further to then refine its actions. Typically, we call this learner a policy that is supposed to optimize sort of some kind of long-term utility or reward function given to it by the environment. And its environment here is typically a simulator, such as the simulator of a game, or simulator of a healthcare logistic problem, or simply a simulation of a human, interacting with an LLM. Now, the problem is this classical paradigm typically relies on trial and error data collection to be able to learn a good policy. So my research starts from this question of understanding how can we reconcile this paradigm? How can we extend this paradigm to build next generation algorithms that are compatible with the current wave of data-driven AI, of machine learning models that are trained on large and diverse data sets. So my research builds these next generation algorithms. And instead of thinking about RL as a pipeline where simply a model or a policy interacts with the world by making decisions and observes consequences, we study the setting where, first of all, these consequences are limited in a way. They're not necessarily reward functions. They might be arbitrary limited feedback given to the model. And secondly, we also consider problems where there's historical diverse data available. So we want to be able to make the most out of the data that already exists and do better via interaction. Also note that this interaction is now no more against a simulator, it's against the real world directly. But that's what we want it to be, because simulators are always, or it's very hard to guarantee that simulators are correct. Now, if you want to realize such a pipeline, there's many questions that come up along different axes. So the first axis is the axis of data. So how can we use offline or historical data sets to train policies that can do better than this data? So how can we do better than simply mimicking what we saw in the data or simply imitating what we saw in the data? The second question is models. So how can we actually extend this sort of a paradigm or extend this paradigm of reinforcement learning to be able to use large scale models and benefit from scaling of compute, scaling of data, scaling of model size, and sort of in general benefit from all the advances that deep learning has made in the last couple of years. And finally, the question of adaptation. So if you're thinking about directly running these models in the real world, how can we make sure that these models can quickly adapt via interaction on the fly to be able to do as good as they can on the problem while interacting with this real world? So the questions of data, model, and adaptation are sort of the three axes along which you can group a lot of the research that we do in this lab. So let me give you some examples of some of this research. So the data axis, some of the work that we did, some of the highlighted work that I'm going to talk about here, focuses on trying to learn policies from offline data only, where you're not allowed access to interacting with the world in a trial and error fashion. So we showed that this involves challenges of distributional shift, and we built algorithms that tackle this problem. And these algorithms actually made their way to downstream application domains, such as in healthcare and in notification systems, where they're actually deployed in products from in recommendation products from different corporations to real users around the world. On the model side, turns out that scaling up model size in the context of RL is not so trivial, because RL fundamentally presents a very different kind of a learning objective than supervised learning. And so some of the work that we've done shows that like sort of the conventionally believed factors that make supervised learning scale really well, such as implicit regularization of gradient descent, these factors may not play a similar supportive role in the context of scaling up model size for reinforcement learning. And so we sort of have done some theoretical work to characterize this and use those theoretical insights to now build better ways of training foundation models or large-scale models with reinforcement learning. So this includes a lot of work that has been going on since the last couple of years, and something that's already still going on, where we are trying to think about how do we combine transformer models or just generally large models with value functions and reinforcement learning techniques in general. And finally, on the adaptation axis, we are sort of interested in the question of how can we quickly adapt in the most sample efficient manner in a real world scenario that we deploy the model in, starting from an initialization that we learned from data. Now we've built algorithms that try to tackle this, many questions that come up as well here, and many questions that are still open in this space. And we've also utilized these insights to improve foundation model training by building methods for training language model agents via multi-turn reinforcement learning, as well as by showing that actually these sorts of techniques of fine-tuning, fast fine-tuning, are really helpful in reasoning problems for LLMs as well, and self-improvement problems for LLMs as well. Okay, so my research overall tries to study a holistic combination of data, model, and adaptation in the context of decision-making systems, with the goal of making models that are generalist as well as can make intelligent decisions on the fly when you deploy them in the real world. So one question that I often get asked is, why should we research this now? So it turns out that there's been a lot of progress with generative models already. And this has led to a lot of advances and a lot of knowledge creation in how do we train models at scale, how do we design architectures, even the kind of data sets that we are training these things on. But these models that are out there still, that are trained with simple generative modeling, are still really bad at making decisions intelligently. If I were to deploy them against in the real world, their performance will start to tank as they keep on interacting more with the world. So my research essentially tries to address this limitation by combining the best of all of these, where it uses these advances, builds on these advances, and devices techniques that can make these models now be good decision makers in the real world to solve problems in over longer horizons of time when these models are deployed. So that's why I think we should precisely research this now, because we can build on a good foundation to actually make machines be useful for the real world in real world problems. So if you're interested to know more about my lab or about any of the works that we are doing or any of the works we have done so far, please don't hesitate to contact me at my email. Thank you for listening.